In this video, we will be introducing geometric vectors. So first, a note on quantities. So we are going to talk about two different types of quantities: scalar quantities that have magnitude only, for example, distance, speed, and mass. And vector quantities, these are quantities with magnitude and direction, for example, displacement, velocity, and weight. So we say that vectors are quantities that require two or more properties to describe them. For displacement, for example, we need to know that the position is a certain distance, 400 meters, and a certain direction, southeast. Or velocity, there is a certain numerical quantity, 13 kilometers per hour, and a direction, which is west. So these things, is the quantity a vector or a scalar? So Will's acceleration when driving, that's a vector because there will be both magnitude, 80 kilometers per hour squared, and direction, northwest. What about the frequency of a note that Vivian plays on her violin? That's simply a scalar. There is just a magnitude. What about Evelyn's age? Also a scalar, magnitude only. And what about the force of gravity? Well, that would be a vector because we have magnitude and direction. So 9.8 meters per second squared down on Earth. And did you know that it's only 1.6 meters per second down on Mars? So next, we are going to focus on geometric representations of vectors. So we can represent a vector with a ray, that is a line segment with an arrow on one end, and the length has to be proportional to the magnitude of the quantity, and the direction has to indicate, well, the direction of the quantity. So this vector AB is a vector that starts at A and ends at B, so we've got the vector AB. Also, we can call its starting point the tail and its ending point the tip or the head. So, can you represent this displacement on a vector diagram? Matilda does cartwheels for 10 meters north, then does backflips for 5 meters west. So, how would you represent that using vectors? Well, it could look like this. And make sure you use a ruler to draw the lines in proportion. So the vertical line that represents her cartwheels should be twice as long as that line going to the west that represents the flips. Okay, so now some more notation. So we already have the notation to describe a vector. You write, we'll formalize it here. So they can be labeled from their beginning and ending points, for example, AB with an arrow over top, or you will also just see a single lowercase letter such as U, so the vector U. And in some cases, you might see just a bold letter like bolded U to represent a vector. So to describe length, the length of the ray or the length of the vector is a positive real number, and that represents the magnitude of the vector. And we can denote the magnitude using absolute value notation, like that. Okay, some common terms. Two vectors are equal if and only if their magnitude and direction are the same. And two vectors are opposite if they have the same magnitude but point in opposite directions. So here we have AB, vector AB, and this is vector BA, so from its starting point to its end. And AB and BA have the same magnitude, but they are pointing in opposite directions. So vector AB and vector BA are opposite, and one is the negative of the other. So you can write that BA is equal to the negative of AB, written as such. So here we have a regular hexagon. That means all 6 sides are equal. and use correct notation to give examples of vectors which are, certain characteristics. So first, equal. There are a number of pairs of equal vectors. For example, FB is equal to EC, or here I've written that AB is equal to ED. So those vectors have the same magnitude and the same direction. So now what about opposite vectors? So opposite vectors are vectors with the same magnitude but opposite direction. So for example, FA and CD have the same magnitude but in opposite direction. And another example, and writing that in the correct format, would be BC is equal to the negative of EF. So that means that they're opposites. So vectors that are equal in magnitude only, so not direction, would be, for example, AF and FE. Because this is a regular hexagon, those two lengths are equal, but they do not have the same direction. So another example would be ED. So the magnitude of ED is equal to the magnitude of DC, and so that's how we write the magnitude. Okay, so describing direction now. So the angle between two vectors is the angle formed when the vectors are placed tail to tail, so like end to end. And that means they start at the same point. And so we can describe this angle theta in different ways, and note that this angle is less than or equal to 180. So one way we can describe it is we can just say the angle between vectors A and B is 45. And to draw that, you would actually need a compass. You would start by drawing vector A, measure out 45 degrees, and draw back vector B. So because position doesn't matter, we could rotate this picture around the screen, but the distance between A and B would always have to measure 45 degrees. So another way of describing direction is by using northeast, south, and west. So we could say that vector A is heading north 40 degrees west. And what that means is you're going north, and then you head, I'm not sure which way's mirrored right now, but looking straight ahead of you, if you go north, and then you will rotate 40 degrees to the west. What that also can mean, if it helps you to think about it differently, is this means 40 degrees west of north. So north, but 40 degrees west of that. And then actually using the protractor, I drew my northeast, southwest grid. And then from the north line, I measured 45 degrees to, I measured 45. Okay, that's incorrect. But I can't change that right now. So, but I would measure 40 degrees in the west direction. Okay. So now scalar multiples of vectors. So for any vector v, negative v, so that's got the same magnitude as v, but in opposite direction. So multiplying by -1 will give you an opposite vector. 2v has the same direction as v, but twice the magnitude. And -3v would have 3 times the magnitude as v and is in the opposite direction. Okay, and these are scalar multiples, so the numbers -1, 2, and -3 are scalars. They're numbers that have only magnitude and no direction. And so vectors which have the same or opposite direction, those are what we call parallel, but we can also call them collinear. And for vectors to be parallel, one must be a non-zero multiple of the other. Okay, we also have the zero vector. It's a vector of magnitude 0 and an undefined direction, and we denote it as 0 with the arrow on top. And then we also have a unit vector, and that's a vector of magnitude 1. And if a vector v is multiplied by a scalar, And if that scalar is 1 over the magnitude of v, then the result is the unit vector that's in the same direction as v. And we write it as v with this symbol called v hat or v cap. And finding the unit vector, that is called normalizing vector v. And so the definition of the unit vector, so v hat, would be 1 over the magnitude of vector v times vector v. So let's say that vector u has a magnitude of 10, and we're going to determine the unit vector for u. So the unit vector will be u hat, and right now it has a magnitude of 10, so for it to have a magnitude of 1, we multiply it by 1 over 10. We multiply the vector u by 1 over 10. Okay, and so now if we have vector A, we are given a bunch of instructions. So we can see that A has a direction that's like due east, and it has a magnitude of 3. So A has, we can write a magnitude of 3. So if we're going to draw the vector B, which is 2 times A, so it's a scalar multiple of A, that means we will draw it in the same direction, but with twice the magnitude. So I need to draw it 6, having a magnitude of 6. So that's my vector B. Vector C is negative 2/3 of vector A. So that means it goes in the opposite direction. So I'll have to point west. And it's 2/3 of the distance. So instead of having a magnitude of 3, it will have a magnitude of 2/3 of 3, which is 2. So I can really draw it anywhere, but I'll just keep going down the row. So it's opposite direction, a magnitude of 2/3. That's vector C. So now D is equal to A. So equal to A means same direction, same magnitude. So I'm just really recopying A. And then E is opposite to A. So opposite means same magnitude, opposite direction. So instead of east, I am going to be going west. F is parallel to A, so that means same direction, usually different magnitude. So I'll just draw something that's heading east when I go all the way to the end, and so that's F. And finally, A cap, that means the unit vector, so I need to go in the same direction as A, but for only one unit, like that. Okay, so that's an introduction to geometric vectors, how to describe its magnitude and position, some other common terms such as equal, opposite, parallel, the definition of a zero vector and a unit vector, and how to normalize vectors.